Good morning, respectable jury, opponent and reviewer. I'm recording co-representative of Belarusian team, and I'm going to present you problem number 3, bouncing flame. Let's first revise the task of the problem. Place a flame, for example, from a Bunsen burner between two charged parallel metal plates. Investigate the motion of the plane. Well, first we decided to divide our report into a few points. First is general points about flame. We should know what substance are we working with. Next is the motion of the flame. We will observe several kinds of motion and we'll give explanations for them. And the last part is dependence on parameters. So let's go to the first point. It's general points about flame. Let's check out what is flame. Flame is a result of chemical reaction between oxygen and fuel. Produce heat which causes light. The gases in the flame become ionizated. Well, we can observe two types of flame, premixed and diffusion. In premixed flame, both oxygen and fuel go from the tube. And when it's premixed, it has a limited volume but high temperature of burning. And when we have diffusion flame, it has higher volume for the same amount of fuel but a lower temperature. In all our experiments, we use diffusion flame. Well, as we said, gases in the flame become ionizated. There is two possible mechanisms of ionization. First is chemical. It's when two substances react between each other, produce another two substances, and one is ion and electron, or possible two ions. And another one is thermal ionization. It happens when ion with when a molecule with high kinetic energy strikes another molecule, and they produce electron and positive ion, for example. Well, here is an example for chemical ionization. And here is, we calculated the average kinetic energy of atoms. And as we see, it's much lower than minimum energy which is necessary for thermal ionization. So we come to conclusion that in our experiments, in our flame, we use mostly chemical ionization. Let's go to the next point, motion. Well, this is our experimental setup. It looks almost like this one. MF of our electrical source is about 9 kilovolts. Its internal resistance is about 0.1 gigaohm. And plate area is 415 centimeters. We used another plate for this experiment. So, as we needed high voltage for our experiment, that's why we can't use a simple battery for it. We put the planes between the plates and let's look what happens. In different, if we change parameters, we can observe three types of motion. First is deflection, another is oscillations when flame touches the plate, and another is oscillations without touching the plate. We will consider all of them. First point is deflection. Due to chemical ionization, we have constant ion income. And well, some of ions will recombine with electrons and other ions. And all other one electron, due to their very high mobility, will fly away from the flame to the positively charged plate. And the all charge which left is almost positive. And positive ions has very low mobility. That's why they have lots of collision with other atoms and move, and they make all the flame move as one body. Well, that's how it's moved to their negatively charged plate. Let's look at this small volume in the flame. Here you can see it. It acts by Archimedean force because its density is much lower than the density of air. Also, it acts by Coulomb force, which we already observed. It moves by such a trajectory, and knowing changing of coordinates, we can calculate, and knowing angle of deflection, we can find ratio between a difference of coordinates, and knowing their dependence on forces, we can take out the dependence between forces. You can see it on the slide. Well, from this dependence, put in angle, Archimedean force, density, and Coulomb force. We can take out the approximative charge of the flame. It's about 2.5 picocoulombs and for about 16 mega electrons. As we see, it's not very big. We will need it later. Here you can see another type of oscillations. Left video is unslowed and right is 14 times slowed, as you see. Well, here is the plot of oscillations. We used a special soft to take points on the border of the flame. And here we can see that maximum deflection of the flame is fixed. That happens because the flame touches the plate, and of course it can't pass through it. Using Fourier transform, discrete Fourier transform, we took out signal frequency spectrum. And in this spectrum we have one main frequency, and it's about 15 Hertz plus minus 2 Hertz. Also we measured amplitude. It's about 2 centimeters with error. Well, what is the mechanism of such a phenomenon? We have our usual flame with ions, some charge of which is 0. Then we apply field, and electrons leave their flame due to their high mobility, and all other charges distribute. You can see it on the picture. Then the flame has a positive, almost positive charge, and it's go to the negatively charged plate. And positive ions recombine at a plate, so the flame become negatively charged. Then it goes back, and by this time, other ions reproduces, and the process goes on a circle. To check our proportions, we collected such an experimental setup. We added 2 resistors with ratio 5000 to 1, and took voltage from the lower one resistance. So here is our experimental setup. Here you can see our flame, plates, and voltage signal. As voltage signals gives us a plot of voltage against time. Well, here you can see the experiments. You can see the voltage curve and oscillation. And here is the plot of coordinate against time, and for the same period of time, it's voltage oscillations. And as we see, the maximum deflection of voltage is just at the moment of time, and it's about 1.5 kilovolts. This changing of charge could be caused only by recombination of the ions of the flame. And knowing this, we can estimate the charge of the flame now. We need for this changing of voltage, capacity, and physical geometrical parameters. And we see that charge grows for about 10,000 times. So we can come to conclusion that charge highly depends on voltage we apply. It happens so because the number of recombinating electrons and ions are lower. So let's come to the last part of this point. It's oscillations without touching the plate. As we also made a plot, and using the discrete Fourier transform, took out frequency. We measured also amplitude, and looking at the amplitude, we can notice that it's not fixed, and it is has some distribution. So it's we couldn't find out how it's dependent on something, but there is something average amplitude, and its error is bigger, as you see. Well, why it's happening so? We understood that if our flame doesn't change its charge by some outside phenomenon, it would just deflect in the field. And well, when it comes to the small distance to the plate, the ions come to the air and recombinate at plate. That's why the flame discharging and the process happened the same as at the previous point. We investigated all types of motions. So now let's look how they depend on parameters. Well, let's check out first a set of variable parameters. First is distance between plates. It will affect Coulomb force, as we said, and also it would affect charge of the flame, as we saw in our experiments. Also, the variable parameter is length of the flame. It's increased the inertia of the flame, which we can call mass, but it would be something very close, but not exactly the same. So let's go to the first plot. Frequency against distance between plates. As we see, if we increase distance, we decrease intensity of the field, so the Coulomb force decreases and charge decreases. Forces are lower, and our frequency is lower, as you see. Here is the frequency against size of the flame. As we see, when we increase the size of the flame, its inertia becomes higher, so it's harder to move it faster. So their frequency decreases with increasing of their length of the flame. Another parameter is amplitude. Here is its dependence of against distance between plates. As we see, when we increase distance, amplitude decreases. That happens so because when we increase distance, forces are lower and maximum deflection is also lower. Well, and here is amplitude, again the size of the flame. You can notice that on this plot, amplitude goes on constant. This number is almost equal to d divided by 4. That happens so because one flame is very big, it starts touching the plate and can't move further. Well, we made all investigations we could, gave explanations, so let's come to conclusion. Flame is hot chemically ionized gas. In electric field, flame changes its charge. High voltage is needed to observe the phenomenon. Oscillations can't be observed without plates, because charge of the flame goes on constant. 3 types of motion can be observed: deflection, in touch oscillations when charge of the flame changed by touching the plate, and oscillations without touch. Well, there is the literature we use, and by the left time we want to show you their phenomenon right now. Okay, now increase the flame. Something wrong with it. Oh yeah, you hear it deflects. We used, and as we see, here is no oscillations and here is oscillates. And that's what we observed in the phenomenon. That's a movable setup, that's why we can't get the same results as we did. So, thank you for your attention.
When you show the flame bouncing on plates, bouncing with touching the plates, does it touch only one plate or does it bounce between the plates?
Well, in fact, we observed the point when it touched one plate, and when the flame became very huge, it started touching both the plates, and there is a very high charge distribution, and it's it's easily to explain why it oscillates, because it's qualitatively the same result, but it's change its charge in different parts of the flame. We have video with really huge flames. We can show it to you. What?
Next question.
Okay.
Yeah. Okay. How did you control the size of the flame?
Well, we used a gas balloon. Well, not this one, just a big gas balloon with a fixer of the amount of flame which comes to
So
us.
you changed the flow of the fuel.
Well, yes, amount of flow of fuel.
Thank you. When you showed the demonstration just now,
Yes.
what would be the popping sound? That
Well, it was because we use another experimental setup, and it has a bit higher voltage, and well, there is something not connected with the flame. Well, you can hear this sound just by turning it on high voltage. Well, I'm afraid it will be error.
All right, thank you. Yeah. Okay. For your software, which points in the flame does it take?
We used a border for point of the flame because it was easier to catch it. Because if we try to take point in the center, we will get error.
All right. Is this the same plate you used to collect?
No,
the
those plates was bigger.
All right, thank you.
there is not enough actually. It's too short. Well, should I take it away?
It's fine. You can take it out.
Okay.
Nice. Thank you, Roger, for your presentation on the bouncing flame. So this is a quick summary of your presentation. Now, the general points for the flame is covered the definition, the type of flame, and the ionization, and the causes of the ionization. The setup was introduced, and the motion was talked about, followed by the deflection was talked about, and the oscillation with without touching. So the following parameters are varied: the distance, flame height, amplitude, and how essentially the various parameters correlate with each other. So these are the strengths and the weaknesses of the reporter's theory. The strength is that the flame is clearly understood very well by the reporter, and he considered many properties of the flames. He also gave very clear explanation of the basics of essentially how a lot of things work. And the weakness is that only diffuse flames were considered and premixed flames were completely ignored. The theory does not actually have any predictive power, and it simply tries to explain what was seen. So it seems like the theory was built on the experiment after the experiment was done. And the theory does not tell us when each phase of oscillation occurs. It merely tries to explain why there are these phases. So the experiment, the strength is that the setup was modified to test for exactly what they wanted to see. And all graphs essentially had error bars, which is obviously always a plus point. And most of the experimental data actually have a theoretical explanation. And the weakness is that certain variables seem to be really hard to measure accurately, and this was not addressed. And the flame's position, we're not sure if the measurement of the flame position is actually good, and only one size of plate was actually tested, and there are some other factors that were not considered. So now I invite okay. Okay, so may I ask you some questions? Now, how large is the actual plate that you used?
The square, as I said, was 415 centimeters. There's radius was about diameter was about more than for about 20 centimeters.
Okay, 20 centimeters. So what is the height of a flame?
Well, height of the flame was varied from a very small flame, or well, it's 2 centimeters.
The largest one.
The largest one was about 8 centimeters.
8 centimeters. So it seems like 8 centimeters might be very, essentially it's in the same order as like 20 centimeters. So do you think things like fringing might be an effect? Perhaps if your flame did not start exactly at the center, then the edges might...
Well, yes, the curves of intensity may influence, but well, we didn't give a quantitative explanation for calculation for our phenomenon, because they are very hard. And qualitatively, it would be observed in with such curves of the field, I can exactly say. So the intensity in the center is the same, so the most of the flame is situated in the parallel intensity field.
Okay, so what do you think might change if, let's say, fringing was an effect and you use larger plates to eliminate the effect while keeping all other factors constant?
Well, if we increase the size of the plate, I think we will get more quality, more straight field. So our phenomenon will be a bit clearer. but qualitatively it wouldn't change anything. And well, if we decrease our place, it of course will give us errors in experiments.
Okay, thank you. I actually agree a lot with this point. I believe that qualitatively there wouldn't be much difference. Alright, so at the start of the presentation, you actually mentioned premixed flames. Why was it not investigated?
In fact, premixed plates goes under the great pressure, and they have very small volume. And observation of the phenomena is very hard on these flames, and we need higher voltage to observe this phenomenon. The maximum deflection will be lower, so oscillations would be hard to observe.
Okay,
we would have to use higher intensity, and well, we was fixed by our current source.
Oh, okay, thank you. So you say that the deflection would be less, but wouldn't, for example, moving the plates closer together, firstly increase the electric field, secondly allow the flame to touch the plates, thus perhaps observing bouncing. So if, let's say, you move the plates together, do you think a premixed flame would bounce?
Well, it should bounce, because all physics mechanisms will be the same, but when we have diffusion flames, premixed flames, we will have higher temperature, and we should take into account their thermal ionization.
So, what do you think is bouncing in the flame?
Well, what is the bounce in the process?
What is the part that is bouncing? Which part of the flame? You mentioned two parts. The ions and the part that is actually ionized and the part that is charged due to thermal energy. Which part causes the bouncing?
Well, okay, we have ions, yes, and well, we doesn't very care what their process that produced ions. We just know that we have ions and electrons.
Okay.
And electrons has very high mobility, and they almost have no collisions while leaving the flame.
May I ask you?
Yes, okay.
What do you think is the yellow part of the flame?
Yellow part of the flame, it's the hottest part of the flame, because in fact
what do you think is made up of?
Well, it's heated CO2.
Why would heated CO2 bounce coherently? I mean, it's a gas, so, and if they are all positively charged, wouldn't it spread out because it's a positively charged cloud of gas that is repulsion?
So, okay, you want to ask me that why ions just simply don't leave the flame?
Well, I mean, if, according to your explanation, the flame is a gas, why does the gas bounce coherently?
Well, okay, this gas consists of simple molecules and ions, yes?
Yes.
And their ions have very low mobility, and they mostly positive. And when they in the electric field they start their motion, they has a lot of collisions with all other atoms. And we have always producing of these ions, and they also try to deflect to their plate. And that's why they move all other ions, all other molecules with them. And that's why we see their motion of the whole flame.
What do you think is molecular density in the flame? Do you think it is actually really likely that one molecule will collide into another molecule in the distance between the plates?
What do you mean?
Because it requires molecular collision for the flame to move coherently, right?
Well, we have our ions, which always move to their negatively charged plate, yes? And some chaotic amount, some chaotic molecules, which amount is in fact in tens in 5 power bigger than amount of ions in approximately. And these ions are enough to move other molecules by the collisions.
Okay,
it's the only process that can happen.
Do you think it is possible that because you know in a premixed flame you don't actually see the yellow part? Why is that so? A premixed flame should be of higher temperature, wouldn't it?
Well, if we look at their plot of their light caused by carbon dioxide on temperature, on the high temperature we will see blue wavelength, and on the temperature we have from their red to yellow.
So do you mean that in a premixed flame the black body radiation is over 10,000 kelvins, is such that the flame can emit blue light even from a non-ionized part? Do you think that is even possible?
Well, I'm sorry, but gases can't be observed like a black body in any approximation, because they have just another spectrum of radiation.
May I propose something? do you think it is possible that the yellow part, instead of being ions like you described, is carbon particles? Because that might explain the coherent behavior. Because if they are the carbon particles, perhaps they will be transferring charges simply via the mechanisms you described.
Well, okay. When our ions produce light only when they recombinate, yes? And when they recombinate, we calculate it for CO2 ions. It's the light they cause, well, the wavelength they cause is at about infrared spectrum. So we can't see it simply.
Okay. Right, let's move on to the next point. What do you think is the impedance of the flame?
What? Can you repeat?
Essentially, what do you think is the resistance of the flame when it bounces?
We made several experiments to measure the current.
Order of magnitude approximation.
Well, as I said, we made several experiments to measure the current. And as we saw now in experiments, the charge of the flame, it highly depends on the voltage we acquire.
So, I mean, when it's bouncing, what would be an order of magnitude of the resistance?
Well,
the charge?
I can show you experiments how we measured the current.
Do you think it's the same order of magnitude as 0.1 gigaohms, which is the resistance of the
well, it highly depends on the distance between plates. When we come very close and have very high flame, its resistance is negligible with our internal resistance. But in our experiments, we doesn't show you such phenomenon, and then its resistance was a lot slower.
But because it seems like from your experiment, when the flame bounces, there's a spike in current, right?
Changing
the
voltage.
Current suddenly increases at one
yes.
point. So doesn't that mean the impedance of the flame will suddenly drop, and that would essentially mean that the rate of the charge transfer to the flame will be limited by your power supply.
In fact, when we have such an experiment, we can look at the flame just an air ball, which have first charge, and then it comes to the negatively charged flame, recharged, goes back.
And but the time it takes to charge will be decreased by the fact that your power supply has
of course, it can't change its charge until it's touched. So it has current only in the moment of touching.
Okay, thank you. When you were doing the demonstration, I noticed that the popping sound actually occurred with this separation when the flame is there. However, when the flame is removed, you had to move the plates much closer before arcing occurs.
Yes, of course. It's easily understand because our flame produces ions, and they, due to chaotic movements of particles, some ions leave the flame. And when we have the whole flame which has some charge and some ions outside, there can be easily caused breakdown between two charged substances.
Do you think the breakdown is between the two plates, or perhaps from one plate to the flame?
It's between one plate to the flame.
So how does that affect your experimental data?
Well, we didn't, as I said, it wasn't the experimental setup we used to make our plots and so on. It was just a small version for demonstration to show you that when we change such parameter as distance, for example, their flame first deflects.
So are you saying that never happens in any of your...
Well, we didn't move the plates so close to cause breakdown in our experiments.
But according to you, it breaks down to the flame. So the flame will move to the plate, right?
Well,
close enough to the plate to cause breakdown? Because it breaks down from the flame to the plate, not between the plates. So the distance between the plates should not matter as long as it's bouncing.
Well, it's mattered because it's affect the charge of the flame. And the bigger the charge of the flame, the more the frequency of breakdown. And if our charge of the flame is low, then the frequency of breakdown is very low, and we almost can't observe it.
Okay. In one of your videos, actually, there seems to be a blue light on the plate. Can you explain what that is? Is there an arc, or is that just some stray light?
Well, I don't remember the blue light, but well.
Okay, never mind. Another question for you explained the ion production in the flame, but why would methane combine with oxygen to form ions? Shouldn't it just form carbon dioxide and water? Where does the OH minus ions come about?
Where ions come from, or what?
No, it just seems like I don't quite understand the equation which you used to describe the ionization. Could you write it down, please?
Well, they are equation or chemical reaction?
The chemical.
Oh, as far as I remember, well, I didn't focus on chemical points. I just took it from the background. It's sorry, I should well applies. Well, it's just an example of chemical reaction which produce ions. There are lots of them for which produce carbon dioxide and electron, for example. There also can be such a reaction.
Okay. Last question. Do you believe? Can you disprove that the yellow part of the flame is made up of carbon particles? Because there seems to be a lot of literature to suggest that.
Well, we used some reference which showed where was the plot experimental gets for one research group that the carbon dioxide on such a temperature gives such a wavelength that causes a yellow light, which is equal to a yellow light.
But
Time is over now.
Okay, thank you.
Questions? Okay. First of all, I have some questions for the reporter. You mentioned that the ionization caused by heat is insignificant compared to the ionization caused by chemical reactions.
Well, it's for our flame because it has a low enough temperature to neglect their thermal ionization.
Okay. So do you realize that in the Maxwell-Boltzmann distribution that with the particles' kinetic energy that there is still a possibility of ionization in the flame even when the temperature is low?
It's possible their ionization, but well, it's a bit higher possible than in the simple air. And well, a chemical is their systemic ionization, and well, thermal is random ionization, which happens with some certain frequency, but it's still not big amount comparing with chemical one.
So on what grounds do you say that the ionization caused by heat is completely negligible?
We used our background. I can show you the book, reference.
Okay. Maybe later. Thank you. And so you considered that the electric field entering your flame was even?
Was what?
Was even, going in the same direction all the time.
Well, it's almost even because our place was in such a size and flame was placed in the center. And there is, as opponent asked me, there was some curves, but they would affect just, well, some small parts of behavior, but quality of the experiment will be the same.
Okay. And you think that the flame we see is heated CO2 molecules?
Yes.
And that the position of the yellow part of the flame corresponds to the distribution of these CO2 particles.
Well, it's just distribution of temperature, in fact.
Temperature.
Yes.
Yes, sir.
Do we know that CO2 actually emits yellow light in the emission spectrum?
It's
okay. Yes, thank you. I know that you guys disagree. Only the questions now.
Все еще не верят, что CO2 выделяет желтый свет.
Do you consider the flame as a conducting body?
Yes, we did it in several experiments, but we didn't show it to you because it has small according to the theory because
so
we
it's
need.
A conductor. Yes.
Yes, it's conductor.
Okay. And do you consider it as a conductor?
I believe so, but not a very consistent one. It can't be described.
Okay. Thank you.
Финальные условия подтвердили, что вот у нас были ссылки, что это не наша идея, что действительно СО2 в этих диапазонах температур испускает желтый свет. Скажи, что точно было. Ты скажи. Я думаю, проверять не буду. Просто подтверди, что это точно есть.
Okay.
Do you mind if I use this space?
Yes, yes, of course.
So I will begin. Good morning, ladies and gentlemen. We are Team Taiwan, and we are here to review problem number 3, bouncing flame. Sorry, am I blocking? No. Okay. Now here's a summary of the report we just saw. First, in the theory, they proposed that combustion causes heat and ionization, which causes the flame that we see. And they discussed chemical ionization versus heat ionization, and decide that chemical ionization is the more important factor. Then in experiments, they chose to use the diffusing flame instead of, they chose to use the diffusing flame to conduct their experiments. And they observed 3 phenomena: deflection, oscillation, and non-touching oscillation. And they changed the parameters of flame length, voltage, and distance. Now, here are some points about the reporter. First of all, in your presentation, you had a clear analysis of the forces working on the flame, like the Archimedes forces and the Coulomb forces, and that helped explain your theory about how the flame moved. And your comparison of displacement and voltage in those 2 charts was very clear as well. And you investigated the cause. You observed the phenomenon and tried to investigate its cause as well as do its parameters. And also you utilized error bars in your charts, and that was very good. However, one thing we saw was that you did not explain the cause. You did not explain in your report the cause of the flame we see. And though you tried to do so when the opponent asked you, your explanation failed to explain the motion. Failed to explain what you saw in the phenomenon. And also, you lack theoretical calculation to support your derived theory. And one thing about your conclusion, your first conclusion was that flame is a hot, chemically ionized gas. Yes, we believe, we think that could be true, but we do not see how your experiment or your project actually proved that or made it one of your conclusions. And your diagram of settle is slightly confusing. The plates were vertical, that's a small thing. And also, you do not consider the distortion of the electric fields caused by the flame, which itself, according to you, is electrically charged. And for the opponent, your short questions were very curt and to the point, and they were followed up by a lot more questions in the later discussion. And you point out the lack of mathematical theory to back up observations. You attempt to isolate parameters for discussion when you discuss them, and you correlate the components. You correlate the components of the flame with its bouncing, which we were very happy to see. And in your discussion, you were continuously trying to introduce the reporter into theoretical ground, step by step. That was very good discussion tactics. However, one thing we would like to point out was that under certain dimensions, the size of the plate actually does not affect the electric field if the voltage applied is the same, and if the plates are large enough. So one of your questions was a little bit, we didn't really see the point of it. And finally, here are some points about the discussion. Your communication and understanding was excellent with each other, and the component of its flame with its relation of the phenomenon is discussed. And however, one thing is that conductive bodies cannot have electric field go through them, which both of you ignored, because if an electric field is going perpendicularly into a conductive body, it will cause a polarization. So for instance, if these are positive ions coming here, the negative ions will go this way, positive ions go this way, and the positive ions will not be able to pass into the thing. And you ignore that. Thank you very much.
Обязательно скажу про то, что презентовали свое решение. Обязательно.
Okay, I really like the discussion and the remark made by the reviewer. I liked in the discussion point of diffusion flame, but well, if we observed, not diffusion but premixed flame, if we use diffusion one, well, that was our third choice. I think that because their tournament lets us to choose how to solve the problem. But as we come from the conclusion, as far from the discussion, as far as I understand, we should just include the pressure, additional pressure, as I think, and also include the thermal ionization. I also, well, I didn't understood what was the problem about taking of points, of border points of the flame, because the layer of the flame goes the same, as you can see in the experiments. So I didn't understood this point. What about also the heat, their light with heat? In fact, when we have heated carbon dioxide, there is two types of heating. It's heat because, two types of radiation. First is radiation because it's too hot, and the second is that the electrons come up to the next level and then falls. And that causes their light we see. Also, we have investigated currency, but opponent didn't let us to show the experiments. I'm not very happy with it, but this happens how it happens. For the proof of the radiation of carbon dioxide, we used really research of a group of scientists, and we didn't took it from our hand. And also for the same was for their choosing of chemical ionization. We didn't take it our hands. We used background reading, and I don't think the opposition on this part was very relevant. Thank you for your attention.
Okay, so please could you attach your presentation back? In the meantime, I just want to ask, because in the task it's mentioned that you should use e.g. a Bunsen burner. Have you ever used a Bunsen burner?
In fact we didn't, but
okay, thanks. And I also wanted to ask a second short question. You calculated with two different means, if I understood, two charges of the flame. One was 16 mega electrons, and the other one was 69 giga electrons.
Yes.
So this is like 3.5 order magnitude difference.
Yes.
So there was a difference between the voltages, or?
Well, we use the same voltage, but we change its distance. And the intensity.
And how much did you change the distance?
In 2 times.
Changing the distance twice means that the charge is changed by 3.5 orders of magnitude.
Yes, it could happen so.
Okay.
As you see now.
I have one question. Did you get a change if you change the position of your flame nearer to one plate, or didn't you?
We did it and it would be an interesting effort. In fact, when we hooked their equipment we used then, we could accurately do this. Now we can't show it because, you see, everything is made by hands and shaken. Well, yes, if we move our flame to their positively charged flame, it can be no oscillations at the same voltage, because our flame wouldn't be able to charge a positively charged, a negatively charged plate, and couldn't recharge itself. And if we move it to, that's all.
I was going to add that I believe their theory is actually sufficient to predict the qualitative phenomenon. If the plate is, for example, in what they say bouncing between 2 plates, perhaps when it moves towards the positive plate, it would change to bouncing against 1 plate, because it would not be able to hit the other side before reionizing.
There's bouncing flame. Do you have any theory about the bouncing and the temperature of your flame?
Can you
Have you any theory about the bouncing of the flame and the temperature?
Well, how connect the bouncing and temperature? Of course, if we increase temperature, we can increase the ionization produces, so we have more ions, the less field is needed to start the oscillations, and and well, there are bigger amplitude with high temperature and then bigger frequency.
What do you mean about this part? Is it right?
I'm sorry, I didn't understand that.
Well, dear juror asked me if I increase just simple temperature of the flame, what will change? And I answered that it would increase amplitude and frequency
And
because ionization will be high.
I believe that there might be another factor in this, namely the thermal ionization. Because as you increase the temperature, I believe the thermal ionization will increase in effect, such that perhaps becoming the dominant effect past a certain temperature.
We still have time. At the beginning, you mentioned something about the mobility of electrons of ions, and that electrons are high mobile. Can you state some numbers? So, what is the mobility of electrons, and what is the mobility of your ions, and which ions?
Well, I'm sorry. Well, I need to try to find some quote in background reading that I took with my help, but I don't remember its numerically. But I well, I can
okay,
throw you a
if not
thought.
number, do you at least know in which, in what is it measured, or
Well, it's
this dimensions?
intensity. Well, it's velocity. Mobility means the velocity in intensity of a field 1 electron volt. Oh, not 1 electron, 1 volt divided by meter.
One last basic question. If you have showed me that electron scope here from the plus, and you have minus, and here is the field.
Yes.
So, or nothing in this way.
Okay. Is direction okay?
Why don't the electrons go to the other side?
Well,
sorry, this is the opposite. Yes.
Well, electrons. Well,
That's the
they go
opposite.
there, and
Yes,
ions
this
go
was
there.
the opposite. But the overall field is the opposite side. Why do they separate? Because there is a field inside here.
Well,
Here, they are contracted together. Why do the electrons go?
Well, they are
this way?
spread all over their flame, and on their border sides of the flame, the interaction between them can be neglected.
The interaction between
Well, okay, we have such a flame, and here is, for example, plus, and here is a minus, and under such a field, it will easily go there. And
but here is a field.
well, here is the field, but well, charge of the flame in most points is lower than the intensity of field caused by charge of the flame is lower.